Swayam Prabha. Digital India. Educated India.
When you have a single independent source in a circuit, it turns out that there are ad hoc circuit techniques which you are probably already familiar with, which will yield the solution. Okay. This is by let us say combining resistors in series and parallel, finally finding a single equivalent resistance across the independent source and then solving for different variables after that. Okay. So, now we will first start from a really simple example and then work our way towards more complicated examples. Okay. Let us say we have a circuit like this, an independent voltage source connected to a resistor. Even before I wrote down the circuit, you know the answer. The current is V by R1. Okay. So, even if you wanted every variable in the circuit, you could tell that very easily. The voltage across this is V, the current is V by R1 in this direction, the voltage here is V and the current is V by R1 in that direction. So, you know the current and voltage across the two branches of the circuit, which are the voltage source and the resistor. Okay. Now, let us say we had something like this. We have a voltage V connected to a series combination of resistors R1 and R2. Okay. And again, by reducing the series combination of resistors into a single resistor, you know that this is the same as that. Okay. A single resistor R1 plus R2. Now, the current through this can be easily solved for. This voltage is V. So, the current here is V by R1 plus R2. And of course, that is the same current that is flowing in the original circuit, that is V by R1 plus R2. Now, of course, you may be asked for anything. You could be asked for this current, in which case you already have it, or you could be asked for this voltage, the voltage across R2, which you can easily find by multiplying the current with the resistance value. Okay. So, the voltage across R2 is nothing but V by R1 plus R2, which is the current, times R2, which is the voltage, times R2 by R1 plus R2. Okay. Now, this is of course, the familiar voltage divider formula, which tells you that if you have a series combination of resistors excited by a voltage V, the voltage across any single resistor is the ratio of that resistance to the total resistance of the series combination times the applied voltage. Okay. So, we have the resistance R2 divided by the total resistance, in this case we have only two resistors, and that whole thing times the voltage V. Okay. So, this is the voltage divider formula. Okay. And if you wanted the voltage across R1, you would have R1 in the numerator instead of R2. Okay. So, again very simple. Now, let us take the case of, let us say, a current source connected to two resistors in parallel, R1 and R2. Okay. So, again you know that this behaves as a current source applied to a single resistor. Now, if we refer to each of these by their conductances G 1, which is 1 by R 1, and G 2, which is 1 by R 2, we know that the conductance of this resistance is G 1 plus G 2, okay, which is 1 by R 1 plus 1 by R 2. So, the resistance of the combination, we also know the formula is R 1 R 2 by R 1 plus R 2. Okay. If we apply a current I, then the voltage that appears across this is simply this I times the resistance value, or this I divided by the conductance value. Okay. So, this voltage is I divided by G 1 plus G 2, which is of course the same as I times R 1 R 2 by R 1 plus R 2. So, sometimes when you have parallel combinations, it is useful to use conductances in the analysis than resistances. Okay. You should get used to both of them, using either conductances or resistances. Now, sometimes some of the expressions look simpler with conductances than with resistances. Okay. So, that is the motivation for using them. So, obviously, the same voltage appears here in the original circuit. The voltage here is I divided by G 1 plus G 2, which is I times R 1 R 2 by R 1 plus R 2. Now, you may be asked for this voltage, in which case we have already solved for it, or you could be asked for currents in individual resistors. So, this current is nothing but the voltage across this resistance divided by the resistance, or the voltage across this resistance times the conductance value. Okay. I will write it in both forms. So, the current here is I times G 1 by G 1 plus G 2. Basically, it is this voltage times G 1, which is the conductance of this, and this can also of course be written as I times R 2 by R 1 plus R 2. In this case, I have taken this expression and divided it by R 1. And similarly, the current through here is I times G 2 by G 1 plus G 2, which is also the same as I times R 1 by R 1 plus R 2. Okay. Now, of course, this is again the familiar current divider formula. The voltage divides in proportion to resistances, the current divides in proportion to conductances. Okay. So, you see that in the voltage divider we had R 1 by R 1 plus R 2, in the current divider we have G 1 by G 1 plus G 2 in the expression for the current through G 1. Okay. Now, normally this is presented as ratios of resistors, in which case you have to take the other resistor, and if you have multiple resistors, you have to take the parallel combination of all the other resistors. So, for the current divider, the formula using the conductances is easier, but of course, you can use either of them. Okay. So, this is again another simple illustration. Now, next we combine these two aspects together and form a circuit which looks like this. We have voltage V, resistance R 1, R 2, R 3, and this is the same as these R 2 and R 3 are in parallel. So, we will have the parallel combination and R 1, and of course, finally, these two are in series and can be reduced to a single resistor. So, we have okay. So, now you can calculate everything from this, that is, first of all, you can calculate the current I, right. So, this is the voltage V, of course. I will be this V divided by the total resistance, and the same I will be here and also here. Okay. And if you want to calculate the voltage across R1, it will be I times R1, which you can easily calculate. Now, at this node, this I divides into two parts. So, some of it goes this way and some of it goes that way, and finally combine. And if you wanted these currents, the currents through R2 plus R3, and you can go back and use the current divider theorem. Okay. So, everything is some repeated combination of series and parallel elements. So, in that case, you can use voltage divider or current divider theorems accordingly and find the solutions. For instance, you have already calculated I. So, the current through R3 would be I times R2 by R2 plus R3. Okay. Let me put this in a different color. So, this is the current through R3, and the current through R2 of course would be I times R3 by R2 plus R3. Okay. So, now the circuit can get more complicated, but you can still go on using this. Okay. You can repeatedly apply this series parallel combinations and simplify the picture to a single resistance across the independent voltage source or independent current source, and find the current or voltage, and from there further calculate using either voltage divider or current divider formulas. Okay. Now, this works for many circuits which have a single independent voltage source, but things can get messy if you have, let us say, things like this. Okay. Then even finding the equivalent resistance that appears across the current source can involve a bit of analysis. So, in these cases, it is probably better to just use the systematic analysis approaches. Okay. So, for instance, you can have even more complications. Okay. So, then even to find the resistance here, you have to resort to systematic analysis approaches. So, you may as well find everything using systematic analysis. Okay. So, in summary, when you have a single independent source, usually by looking at series parallel combinations in the circuit, you will be able to get a single equivalent element across the voltage or current source, and from there progressively solve for everything you want. Okay.